At 10:02 in the morning on August 27, 1883, a sound was born that the human race had never heard before. It crossed the Indian Ocean without losing its voice. It reached Australia, and people there looked toward the seas searching for a ship in distress. It crossed the Bay of Bengal. It reached an island near Mauritius, 4,800 kilometers away, and a British officer wrote in his log that he could hear what sounded like heavy artillery firing from somewhere beyond the horizon. Sound circled the earth, not once. 7 times. No weapon ever built by human hands has been heard across 1/13 of the surface of this planet. No explosion in the history of warfare has sent a pressure wave measurable on barometers from London to Washington. No event in recorded human experience has rewritten the geography of a coastline, altered the temperature of the entire planet, and killed 36,000 people, most of them not by fire, not by ash, but by the sea itself rising and erasing everything it touched. This was not a disaster. The word is too small. This was the Earth demonstrating, without apology and without warning, what it is capable of when it decides to speak at full volume. The people of the Sunda Strait went to sleep on the night of August 26, 1883. Beside a sea they had known all their lives. They did not know that beneath the island, sitting quietly in the middle of the water, a geological sequence had already begun that nothing in the universe was going to stop. By the following afternoon, the island was largely gone, and the world, the actual, measurable, physical world, was permanently different. This is the story of Krakatoa, the loudest sound in human history, the wave that erased the coast, the explosion that the planet itself could not contain. Stay with us, because understanding what happened that morning changes the way you hear every silence that follows it. Before we take you back to that morning in 1883, if stories like this one matter to you, take 5 seconds right now. Subscribe to Fury of the Earth and hit that like button. It is the simplest way to tell us that this kind of storytelling is worth continuing, and it helps us bring the next chapter of our planet's extraordinary history to people who are ready to listen. Welcome to Fury of the Earth, the world before the fire. In the summer of 1883, the world was still young enough to believe it had seen its worst days. The industrial age was rewriting the rules of civilization. Steam engines crossed continents. Telegraph wires carried voices across oceans. The British Empire stretched its shadow over a quarter of the globe, and in drawing rooms from London to Batavia, educated men spoke with quiet confidence about the mastery of nature. Science, they believed, had finally tamed the earth beneath their feet. They were wrong. Nowhere was this confidence more misplaced than in the Dutch East Indies, the sprawling constellation of islands that would one day become Indonesia. Under colonial rule, the archipelago had become one of the most profitable corners of the world. Spices, coffee, rubber, and sugar moved through its ports in vast quantities, feeding the appetites of European markets. Batavia, the colonial capital on the northwestern coast of Java, was a city of wide canals, whitewashed buildings, and the unhurried rhythms of tropical administration. Life there moved to the cadence of trade winds and monsoon seasons, and the enormous wealth flowing through its harbor gave the city an air of permanence, even invincibility. But the Dutch East Indies sat on something far older and far more powerful than any empire. The Indonesian archipelago occupies one of the most geologically violent regions on Earth. Beneath its green mountains and turquoise waters, the great tectonic plates of the Indo-Australian and Eurasian systems grind against one another in a slow, relentless collision that has been ongoing for tens of millions of years. This collision built the islands themselves, raising volcanic peaks from the seafloor over vast stretches of geological time. It also created what geologists now call the Sunda Arc, a curving chain of volcanic islands, stretching from Sumatra through Java and beyond. Each one a monument to the fires burning deep within the planet. The Sunda Strait lies at the hinge of this arc, the narrow channel of water separating Sumatra from Java. It is one of the most strategically important waterways in Asia, a corridor through which ships have passed for centuries, carrying goods between the Indian Ocean and the South China Sea. Sailors knew the strait well. They knew its currents, its weather patterns, and the silhouette of its islands. Among those islands, rising from the blue water roughly midway between the two great landmasses, sat a volcanic island that had been a familiar landmark for generations. Its name was Krakatoa in 1883. Krakatoa was not unknown to science or to history. The island had erupted before. Dutch records going back to the 17th century noted periodic activity, and a major eruption in 1680 had reshaped its profile and left behind a landscape of ash and hardened lava. But in the decades that followed, the volcano had settled into silence. Vegetation crept back across its slopes. Forests thickened. The island became, in the popular imagination, simply another green peak rising from the strait, scenic, remote, and unremarkable. By the early months of 1883, Krakatoa consisted of 3 overlapping volcanic cones on a single elongated island. The largest was Krakatoa, a steep-sided peak rising roughly 800 meters above sea level. To its north stood Danan, and beyond that the smaller cone of Paroxysmal. The island was uninhabited, too rugged and too remote to support a permanent settlement, but it was not entirely unvisited. Ships passed close enough to see it clearly, and a handful of scientific expeditions had landed on its shores over the years. In May of 1883. The first warnings began on the 20th of May. The captain of a German warship passing through the Sunda Strait reported unusual activity. A cloud of ash and steam rising from the northern end of Krakatoa. A low, rhythmic rumbling that his crew could feel more than hear. The observation was logged, passed along through official channels, and noted with mild scientific interest. It was not, at the time, considered alarming. Volcanic activity in the region was not unusual. The Sunda Arc was dotted with active and semi-active peaks, and minor eruptions were an accepted feature of the landscape, but the activity did not stop. Throughout May and into June, the eruptions at Krakatoa continued to intensify. Columns of ash rose several kilometers into the air. Sailors reported pumice floating on the surface of the strait in large quantities, a sign that magma was reaching the water. The sounds of the eruptions, described variously as deep cannon fire or rolling thunder, could be heard on the coasts of Java and Sumatra. Residents of coastal towns noted the noise but went about their lives. The colonial administration in Batavia took note. A scientific party was organized and dispatched to the island in late May to observe and report. What they found was extraordinary. Paroxysmal, the smallest of the 3 cones, had opened a vent and was erupting almost continuously, throwing ash and steam to heights that astonished the observers. The air smelled of sulfur. The ground trembled underfoot. Trees closer to the vent had been stripped of their leaves. The scientists took measurements, made sketches, and returned to Batavia with observations that were by the standards of the day. Remarkably detailed, their report noted the scale of the activity but stopped well short of alarm. Volcanic eruptions, they understood, were common events in this part of the world. They could intensify. They could also subside. History offered examples of both. What history could not offer? What no living person had witnessed? And what no scientific framework of the era could fully anticipate, was what Krakatoa was actually preparing to do. Beneath the island, forces that had been building for centuries were approaching a threshold. The magma chamber feeding the volcano was not simply refilling. It was reorganizing. The geological structure of the island itself was being stressed in ways that would, within a matter of months, produce an event so far outside the boundaries of human experience that it would require entirely new scientific vocabulary to describe. The summer of 1883 had barely begun, and the Earth was already holding its breath. The mountain peaks, by the time June arrived, Krakatoa had stopped being a curiosity and had begun to become a presence. The eruptions that had begun in May were not fading. They were evolving. The column of ash rising from Paroxysmal grew taller and denser with each passing week, visible from the coastlines of both Java and Sumatra on clear days. Ships crossing the Sunda Strait now gave the island a wider berth, not out of official instruction but out of instinct. Sailors who had spent their lives reading the sea and the sky understood, in the wordless way of experienced men, That something about Krakatoa had changed. The sounds were the first thing most people noticed. Along the western coast of Java. In towns like Enyer and Merak, residents had grown accustomed to a low, persistent rumbling that seemed to come from the direction of the strait. It was not constant. It rose and fell, sometimes disappearing for hours before returning with renewed intensity, but it was always present in some form, a reminder that the island to the west was not sleeping. Fishermen described it as a drumbeat beneath the water. Children in Enyer reportedly pressed their ears to the ground to hear it better. For most people, however, the sound was simply absorbed into the background of daily life. The way any persistent and non-threatening phenomenon eventually becomes ordinary. In Batavia, the colonial capital, the reaction was more measured but no less attentive. The scientific community in the city was small but engaged, and the eruption of Krakatoa had become a topic of genuine interest among the educated class. The Natural Sciences Society of the Dutch East Indies, based in Batavia, had already received the report from the May expedition and was monitoring the situation with careful attention. Letters moved between Batavia and Amsterdam, between field observers and academic institutions in Europe, carrying descriptions of the activity and cautious interpretations of its significance. What those letters could not convey was the scale of what was actually happening beneath the island. Modern volcanology, informed by seismic monitoring and satellite observation and a century of accumulated research, understands the processes at work beneath a stratovolcano with a precision that the scientists of 1883 simply did not possess. They knew in broad terms that volcanoes were produced by the movement of molten rock from depth toward the surface. They understood that eruptions could be explosive or effusive, violent or gradual. But the internal mechanics of a volcano, the dynamics of magma chambers, the role of dissolved gases, the catastrophic potential of a collapsing caldera remained largely beyond the reach of the science of their era. What was happening beneath Krakatoa in the summer of 1883 was this. Magma rising from deep within the earth was encountering the existing volcanic structure of the island, a structure that had been in place for centuries and was in critical ways compromised. The three cones of Krakatoa, Rakata, Danan, and Perboawatan, sat atop a much older and larger volcanic system whose history stretched back hundreds of thousands of years. That ancient system had left behind a network of voids, fractures, and weakened rock formations within and beneath the island. As fresh magma pushed upward into this structure, it was not simply filling a chamber. It was infiltrating a complex and fragile architecture. The gases dissolved within the rising magma were central to what would follow. Magma that originates at great depth carries within it enormous quantities of dissolved gases, primarily water vapor, carbon dioxide and sulfur dioxide, held in solution by the immense pressure of the overlying rock. As the magma rises and pressure decreases, those gases begin to exsolve, separating from the melt the way carbonation separates from a pressurized bottle when the cap is removed. In a volcano with open vents in a relatively fluid magma, this process is gradual and manageable. The gas escapes, the magma moves upward, and the eruption proceeds in a relatively controlled fashion. But Krakatoa's magma was not particularly fluid. It was silica-rich and viscous, the geological equivalent of cold syrup, and it did not allow gas to escape easily. As the magma rose through the late spring and into summer, gas pressure built within it, trapped and accumulating. Like a breath held for far too long, throughout June and July, the visible activity at the surface reflected this building pressure in ways that observers recorded with increasing attention. New vents opened on the island. The eruption column from Perboawatan was joined by activity from Danan, and occasional outbursts from the flanks of Rakata itself suggested that the entire volcanic system was becoming involved. Ashfall was reported on ships at considerable distances from the island. The quantity of pumice floating in the strait continued to increase. In Batavia, the sky on certain evenings took on an unusual haze, and the sunsets were described as exceptionally vivid, a consequence of the fine ash and sulfur aerosols already entering the upper atmosphere. The telegraph network connecting the Dutch East Indies to Europe carried news of the eruption to a wider world, and for a brief period Krakatoa attracted the attention of the international scientific community. Observers as far away as Australia noted the unusual atmospheric conditions. In England, scientific journals published correspondence from Dutch East Indies observers describing the activity. The general consensus among those who wrote and read these reports was that the eruption was significant but not unprecedented. Volcanoes erupted. This one was erupting more dramatically than most. It would eventually quiet down. That confidence was not entirely unreasonable given what history provided. But history, in this case, was an imperfect guide. The island that observers were watching in the summer of 1883 was not simply a volcano in eruption. It was a geological system approaching a point of no return, a threshold beyond which the processes set in motion could not be reversed or arrested. Only completed. August arrived with brutal heat and heavy tropical skies. On the island, the ground shook almost continuously. The eruption columns reached heights that made earlier observations seem modest by comparison. The sounds carried across the water with a new quality, sharper, more percussive, more urgent. Nobody in the coastal towns of Java and Sumatra understood what that change in sound meant. In less than 3 weeks. They would. The architecture of catastrophe to understand what Krakatoa was about to do. It is necessary to go back much further than 1883. Further even than the eruption of 1680 that Dutch sailors had recorded in fading logbooks. To understand what was coming, it is necessary to go back hundreds of thousands of years, to a time when the island that would become Krakatoa did not yet exist in any recognizable form. The Sunda Strait sits above one of the most geologically active subduction zones on Earth. Here, the Indo-Australian plate moves northward and slides beneath the Eurasian plate at a rate of roughly 6 centimeters per year, a pace that sounds almost gentle, until one considers that it has been continuing without interruption for tens of millions of years. As the descending plate sinks deeper into the mantle, the immense heat and pressure cause it to release water and other volatile compounds into the overlying mantle rock. Those volatiles lower the melting point of the surrounding material, generating magma that rises buoyantly toward the surface. This is the engine that built the Sunda Arc and every volcano along it. This is the engine that built Krakatoa. The island that existed in 1883 was not the original volcanic structure at that location. Geologists now believe that a much older and vastly larger volcano, sometimes called Proto-Krakatoa, occupied the same site in the distant past. At some point in the geological record, estimates range from tens of thousands to several 100,000 years ago, that ancient volcano experienced a catastrophic collapse. Its magma chamber emptied during an enormous eruption, and the overlying structure, robbed of its support, fell inward upon itself. The result was a caldera, a great circular depression, much of which now lies beneath the waters of the strait. The island of Krakatoa, as it existed in 1883, was, in geological terms, a relatively young structure built atop the remnants of that ancient collapse. The 3 cones, Rakata, Thanan, and Perboawatan, had grown up within and around the edges of the older caldera over subsequent centuries of volcanic activity. They were, in a meaningful sense, a new volcano growing inside the ruins of an old one. And the old ruins were still there beneath them. A hidden landscape of fractured rock and ancient voids that would play a decisive role in what was coming. The critical vulnerability of Krakatoa's structure in 1883 lay in this layered geology. The newer cones sat atop material that was not uniformly solid. The ancient caldera walls and the debris of the protovolcanic collapse created zones of weakness within the island's foundation, pathways along which water could move, fractures along which pressure could propagate, boundaries where different rock types met with different densities and different responses to stress. Water was the element that would turn a large volcanic eruption into something almost incomprehensibly violent. The Sunda Strait is shallow in many places around Krakatoa, and the island's coastline in 1883 was relatively low-lying in its northern portions. As the eruptions of May through July opened new vents and fractured the surface of the island, they created pathways through which seawater could potentially interact with the rising magma. The interaction of seawater with molten rock produces what volcanologists call a phreatomagmatic reaction, an explosion driven not by the gas content of the magma alone but by the instantaneous conversion of water to steam at temperatures and pressures that exceed anything a surface environment would normally produce. When cold seawater contacts magma directly, the water flashes to steam with a volumetric expansion so rapid and so extreme that the resulting explosion can be orders of magnitude more powerful than the volcanic eruption alone. In August of 1883, Krakatoa possessed every ingredient for exactly this kind of catastrophic interaction. The magma was gas-rich and viscous. The island's structure was fractured and compromised. The sea was immediately accessible through multiple pathways, and the pressure building within the volcanic system had been accumulating for months, what no observer could see, and what no instrument of the era could measure, was the precise state of the magma chamber at depth. Modern volcanologists, working backward from the evidence left behind by the eruption, have estimated that the magmatic system beneath Krakatoa in August 1883 had reached a condition of extraordinary instability. The pressure differential between the interior of the system and the surface had grown to a point where any significant disruption, a major collapse of the vent structure, a large influx of seawater, a sudden failure of the overlying rock, could trigger a cascading sequence of events that would be, once initiated, impossible to stop. The mountain had been speaking for 3 months. It had been speaking in ash columns and tremors and the sulfur smell carried on the wind across the strait. It had been speaking in the unusual sunsets visible from Batavia and in the pumice fields drifting slowly toward the Javanese coast. On the morning of August 26, 1883, it stopped speaking, and it began to scream. The first day of the end, August 26, 1883, began as an ordinary Sunday in the Dutch East Indies. In the coastal towns along the western shore of Java, people went about the slow rhythms of a tropical morning. Markets opened. Fishing boats moved out into the strait. In Enier, one of the closest inhabited points to Krakatoa, children played near the waterfront while their parents attended to the unhurried business of a colonial Sunday. The rumbling from the direction of the island had become so familiar over the preceding months that most people had simply stopped hearing it as a warning. It was background. It was the world as it had been for weeks. At approximately 1 o'clock in the afternoon, that changed. A series of explosions began at Krakatoa that were unlike anything the preceding months of activity had produced. The eruption column that rose from the island in the early afternoon of August 26th climbed to an estimated height of 27 kilometers, well into the stratosphere, carrying with it billions of tons of pulverized rock, ash, and volcanic gases. The sound of the initial explosions reached Batavia, more than 160 kilometers to the east, with enough force to rattle windows and send residents into the streets in confusion. Ships in the strait reported darkness, falling over the water in the middle of the afternoon as the ash cloud expanded outward from the island in every direction, blotting out the sun across a vast area. The eruption of the afternoon of August 26th was, by any historical standard, an extraordinarily powerful volcanic event. Had it ended there, it would still have been recorded as one of the most significant eruptions of the 19th century. The ashfall alone caused significant disruption across a wide area. Pumice rained down on ships caught in the strait. The telegraph operator in Enier sent dispatches to Batavia describing the sky turning black at midday and the air filling with the smell of sulfur so thick it was difficult to breathe, but it did not end. There. Through the afternoon and into the evening of August 26th, the eruptions continued with escalating intensity. A series of distinct explosive events punctuated the continuous roar of the ongoing eruption, each one sending fresh columns of material into the atmosphere and generating pressure waves that observers felt as physical sensations: a compression in the chest, a ringing in the ears, the involuntary flinch of a body responding to something the mind had not yet processed. The eruptions generated lightning within the ash column, great crackling discharges of static electricity that illuminated the cloud from within, visible from the Javanese coast as an eerie, pulsing light on the western horizon. On the water, conditions had become genuinely dangerous. The strait was now covered in a thick layer of floating pumice in many areas, making navigation difficult and, in some places, impossible. Ships that had been caught in the strait when the eruption intensified found themselves moving through a landscape that had transformed entirely, the water gray and choked with debris, the sky dark with ash, the air filled with a constant deep vibration that seemed to come from everywhere at once. The crews of these vessels, some of whom left detailed accounts that would later be compiled by the Royal Society of London, described a profound sense of unreality. The world they had sailed into that morning no longer existed. The ashfall reached Batavia by evening, coating the city in a fine gray powder that drifted through windows and settled on the broad leaves of the garden plants that colonial residents cultivated with such care. The city's gas lamps, lit early because of the premature darkness, gave the streets an amber glow through the settling ash. People stood on their verandas and watched the western sky pulse and flicker with the distant light of the eruption. Some were frightened. Many were simply transfixed. What no one in Batavia and no one in Enier or Merrick, or any of the coastal towns facing the strait, understood was that the eruption they were witnessing was not the event itself. It was the preparation for the event. The explosions of August 26th, enormous as they were the volcanic system clearing its throat. They were the preliminary discharge of a system under pressure that had not yet found its true release. Beneath the island, the explosions of the afternoon had done something far more consequential than simply ejecting material into the atmosphere. They had begun to structurally compromise the island itself. Each major explosion removed material from the volcanic edifice, reducing the mass and pressure bearing down on the magma chamber below. As the overlying rock was blasted away and the vent structure was widened and weakened, the chamber below became increasingly exposed, a pressurized system with a diminishing cap. The sea was close. The fractures were widening. The pressure was immense. Through the night of August 26th, the eruptions continued without pause. Those few people who managed to sleep did so to the sound of continuous thunder from the west, interrupted by periodic concussions that shook the walls of their homes and sent objects falling from shelves. Many did not sleep at all. They sat in darkness and waited, uncertain for what dawn was still hours away, when the volcano entered the final sequence of events that would define its place in history. The morning of August 27th was coming, and with it, the end of the world as that corner of the earth had known it. 4 explosions. That shook the world. The morning of August 27th, 1883 produced 4 explosions. That sentence, stated plainly, does not begin to convey what those 4 events actually were. The word explosion belongs to the vocabulary of human experience. A gas main rupturing, a building demolished, a munition detonating. It carries with it a scale that the human mind can hold and process. What happened at Krakatoa on the morning of August 27th requires the word only because no better one exists. In reality, each of those 4 events was a geological detonation of a magnitude that had no precedent in recorded human history. The first explosion occurred at approximately 5:30 in the morning. It was large enough that, under ordinary circumstances, it would have been the defining event of the eruption, a catastrophic discharge that sent material high into the stratosphere and generated a pressure wave detectable across a significant portion of the globe. On the morning of August 27th, it was merely the opening movement. The second explosion followed at approximately 6:44. Larger than the first, it drove a fresh column of ash and gas to extraordinary heights and sent a new surge of pyroclastic material, cascading down the flanks of the island toward the sea. The water around Krakatoa, already choked with pumice and debris from the previous day's activity, received this new material with a violence that generated waves along the coastlines of the strait. In Enier and the other coastal settlements facing the water, the sea had been behaving strangely since the previous afternoon, pulling back from the shore in the manner that those with experience of such things recognized as deeply wrong, then surging forward with unusual force. These oscillations were the early signatures of tsunamis being generated by the eruption, and they had already caused damage and fear along the low-lying coastlines. But they were not yet the catastrophe. The third explosion, at approximately 8 o'clock, was significantly more powerful than either of its predecessors. Modern volcanological analysis, using the evidence preserved in the geological record and the barometric readings taken at stations around the world on that date, has estimated this explosion as one of the largest discrete volcanic events in the entire sequence. It generated a tsunami wave of considerable size that struck portions of the Javanese and Sumatran coastlines and caused significant casualties and destruction. The towns along the western coast of Java were battered. Ships in the strait were lifted and thrown. The darkness over the water, which had persisted through the night, deepened further as fresh material was driven into the atmosphere. And then, at 10 minutes and 2 seconds past 10 o'clock in the morning, the fourth explosion occurred. What happened at 10:02 a.m. on August 27, 1883, was the paroxysmal eruption of Krakatoa, the single largest explosion in recorded human history. The event involved the near-simultaneous discharge of an almost incomprehensible volume of material, the catastrophic collapse of the northern portion of the island into the emptied magma chamber below, and the violent interaction of that collapsing structure with the seawater flooding into the void. The result was an explosion so powerful that it has never been exceeded by any volcanic event witnessed and measured by modern science. The sound traveled at the speed of sound through the atmosphere, roughly 340 meters per second, and it did not stop. It crossed the Indian Ocean and reached the coast of Australia, where residents of towns in Western Australia reported hearing what they described as artillery fire or cannon shots and sent search parties looking for ships in distress. It crossed the Bay of Bengal and was heard on the Andaman Islands. It reached the island of Rodriguez near Mauritius, more than 4,800 kilometers from Krakatoa, where the British chief of police logged reports of what seemed to be the sound of heavy guns firing from the direction of the sea. The sound of Krakatoa's final explosion was heard in total across an area covering approximately 1/13 of the entire surface of the Earth, a listening audience of geography that no human voice, no instrument, no weapon ever constructed has come close to matching. The pressure wave generated by the explosion traveled through the atmosphere not once but multiple times. Barometers at meteorological stations around the world recorded the passage of this wave as it circled the globe, 7 times in total. Detected at stations as far from the Sunda Strait as England, France, and the United States. Scientists at the time were initially uncertain what they were seeing in their instruments. The idea that a single geological event could send a measurable pressure pulse around the entire planet was, in 1883, almost beyond scientific imagination. The column of material ejected by the paroxysmal explosion reached an estimated height of 80 kilometers, well into the mesosphere. Far above the altitude where weather occurs, far above the altitude reached by any of the preceding explosions. The volume of material discharged in the eruption sequence as a whole has been estimated at approximately 21 cubic kilometers of dense rock equivalent. The energy released by the paroxysmal explosion alone has been calculated at roughly equivalent to 10,000 times the energy of the atomic bomb detonated over Hiroshima, but it was not the sound, and not the pressure wave, and not the column of ash reaching towards space that killed the people of the Sunda Strait. It was the water. The collapse of Krakatoa's northern flank into the sea displaced the ocean in a manner so sudden and so violent that it generated a series of tsunami waves of extraordinary height and speed. These waves radiated outward from the point of collapse and struck the coastlines of Java and Sumatra within minutes, moving too fast to outrun, arriving without warning in places where the people had no elevated ground to reach and no understanding of what the receding sea at their feet actually meant. The wave that struck Enier and the surrounding coastline reached heights estimated between 15 and 30 meters in places. It arrived and it consumed everything in its path: buildings, boats, trees, people, with a completeness that left almost nothing standing and almost no one to describe what had happened. The morning of August 27th was not yet half over. The wave that erased the coast, the tsunami, did not announce itself. That is the detail that survivors, in the weeks and months that followed, returned to again and again in their accounts. There was no gradual building of the water. There was no visible wall approaching from the horizon that might have given a person time to turn and run. In most places along the western coast of Java and the southern coast of Sumatra, the wave arrived as a sudden, total transformation of the world, the sea becoming something it had never been before. moving in a direction and at a speed that belonged to no natural experience any living person in those towns had. Accumulated. The coastline of the Sunda Strait in 1883 was densely inhabited by the standards of the region. The towns and villages facing the water had grown up over generations around the twin economies of fishing and trade, and their relationship with the sea was intimate and largely benevolent. The strait provided food, connected communities, and carried the commerce that sustained colonial and local life alike. People built close to the water because the water was their livelihood. The low-lying coastal geography that made these settlements so vulnerable to what was coming was the same geography that had made them desirable places to live for centuries. Enier was among the largest of the coastal towns directly facing Krakatoa across the strait. It had a lighthouse, a telegraph station, a harbor, and a population that had spent the previous day and night listening to the eruption with a mixture of anxiety and fascination. The telegraph operator in Enier had been sending dispatches to Batavia throughout August 26th, providing one of the most detailed real-time records of the eruption's progression. His final message, sent in the early hours of August 27th, described continuing heavy activity from the direction of the island. After that message, the telegraph line from Enier went silent. It never transmitted again. The wave generated by the paroxysmal collapse of Krakatoa's northern flank traveled across the strait at speeds consistent with the depth of the water in the open strait, moving at hundreds of kilometers per hour, slowing as it entered shallower coastal waters but losing none of its energy, simply concentrating it upward into height. The wall of water that reached Enier has been estimated by researchers at between 20 and 30 meters in places along the coastline, a height that placed the crest of the wave well above them. Rooftops of every building in the town of Enier was destroyed completely. Not damaged, not partially swept, erased from the geography of the coastline with a thoroughness that left investigators, arriving in the days that followed, struggling to identify where the town had actually stood. The lighthouse, a substantial masonry structure built to withstand the ordinary violence of tropical weather, was demolished. The harbor disappeared. The streets, the buildings, the market, the colonial administrative offices, all of it was taken by the water and redistributed across a landscape that bore no resemblance to what had existed hours before. Merak, to the north of Enier, was similarly obliterated. Tyringen, Seringo, Bentham, the wave moved up the coast with mechanical indifference, entering each settlement and removing it. In some locations, the topography of the coastline focused and amplified the wave's energy, driving water inland to distances that survivors found difficult to believe, and that early investigators initially doubted before the physical evidence confirmed them. Trees were stripped of bark by the force of the moving water. Debris was carried kilometers inland and deposited in locations so unexpected that the task of understanding what had happened required weeks of systematic examination. On the Sumatran side of the strait, the damage was similarly catastrophic. The town of Teluk Beton, situated at the head of a bay that funneled and amplified the incoming wave, was struck by water of exceptional height and force. A Dutch government ship, the Beru, was carried inland by the tsunami and deposited in a river valley approximately 3 kilometers from the coast and nearly 10 meters above sea level, where its hull came to rest among the debris of the forest. The image of a steel-hulled ship sitting in a jungle valley, far from any navigable water, became one of the defining photographs of the disaster's aftermath, a single image that communicated, more effectively than any written description, the scale of what the water had done. The death toll from the tsunamis generated by Krakatoa's eruption has been estimated at approximately 36,000 people, though some historical analyses place the figure higher. The majority of these deaths occurred not from the eruption itself, not from the ash, or the pyroclastic flows or the direct effects of the explosion, but from the water. The sea, which had sustained these communities for generations, became in the space of a few minutes the instrument of their destruction. The waves were not finished with a single strike. As the tsunami energy reflected off coastlines and interacted with the complex underwater topography of the strait, secondary waves continued to arrive for hours after the initial impact. Survivors who had managed to reach higher ground watched the sea surge and recede repeatedly through the morning and into the afternoon of August 27th, each surge carrying with it the debris of what had been towns and villages and returning it, transformed and broken, to different parts of the coast. In Batavia, the news arrived slowly and incompletely through the damaged telegraph network. Reports spoke of enormous destruction along the western coast, of towns that could not be contacted, of ships reporting extraordinary conditions in the strait. The full picture of what had happened would not be assembled for days, as relief expeditions made their way along a coastline that had been fundamentally remade. What they found when they arrived exceeded the worst of what anyone in Batavia had allowed themselves to imagine. The coast of the Sunda Strait, on the morning of August 28, 1883, was a different place than it had been 2 days before. Not metaphorically. Literally. The geography had changed. The maps were wrong. And Krakatoa itself, the island that had stood in the middle of the strait for as long as any record existed, was largely gone. The silence after the fire, when the eruptions finally subsided in the late afternoon of August 27, 1883, the Sunda Strait entered a silence that those who experienced it described as profoundly unnatural. For nearly 4 days, the region had existed under a continuous acoustic assault. The rolling thunder of the eruptions, the crack and percussion of individual explosions, the deep vibration that residents of coastal towns had felt in their bones as much as heard with their ears. The sudden absence of that sound was not experienced as relief, it was experienced as wrongness. The silence had a quality that survivors found difficult to articulate but consistently attempted to describe, a heaviness, an emptiness, as if the world had exhaled something essential and not yet drawn breath again. The sky above the strait remained dark for days. The ash and aerosol cloud ejected by the paroxysmal explosion had spread through the upper atmosphere with extraordinary speed, carried by stratospheric winds across the Indian Ocean and beyond. At ground level, the air was thick with fine ash that settled slowly and continuously on every surface, on the water, on the ruins of coastal towns, on the leaves of surviving vegetation, on the upturned faces of people trying to understand what had happened to their world. The sun, when it was visible at all through the haze, appeared diminished and strange, described by observers as blue or green in color, a consequence of the way the suspended particles in the atmosphere scattered light of different wavelengths. Where Krakatoa had stood, there was now mostly water. The paroxysmal explosion and the caldera collapse that accompanied it had removed approximately 2/3 of the island's original landmass. The northern cones, Perbo-Owatan and Danan, had ceased to exist as geographical features. Krakatoa, the southernmost and largest of the 3 original peaks, survived but was dramatically altered. Its northern face had been sheared away by the collapse, exposing a vertical cliff of fresh rock that dropped directly into the sea. What remained of Krakatoa rose from the water as a truncated, asymmetrical remnant, its exposed interior a cross-section through the geological history of the volcano. Layers of lava flows and ash deposits laid down over centuries, now visible to the open sky for the first time. The caldera that had formed beneath the collapsed northern section of the island lay underwater, a depression on the seafloor reaching depths of roughly 270 meters, below sea level in places, where solid land had stood above the waterline just days before. The volume of material involved in this collapse, the rock and magma that had either been ejected into the atmosphere or had fallen inward into the emptied chamber below, was staggering by any measure. The strait itself had been reshaped. Underwater topography that ships had navigated by for generations had changed. Depths that charts recorded as reliable were now unreliable. The physical geography of one of the most traveled waterways in Asia had been rewritten in a single morning. The immediate human task of reckoning with this transformation was immense and, in many ways, heartbreaking. Relief expeditions dispatched from Batavia in the days following the eruption moved along a coastline that bore almost no resemblance to the charts they carried. Landmarks were gone. The lighthouse at Enier, which had guided ships through the strait for years, no longer existed. Entire settlements that appeared on colonial maps had been removed so completely that expedition members struggled to confirm their locations. In some areas, the eruption and the subsequent tsunami had deposited so much material, ash, pumice debris that the coastline had actually advanced into the sea, new land created from the destruction of everything that had been built upon the old. The survivors they found were, in many cases, in states of shock that the medical understanding of the era had limited vocabulary to describe. People had watched their families disappear into the water. They had been carried by the wave and deposited, living in locations they could not explain. Some had survived by clinging to debris, spending hours in water filled with hot pumice before being found. The physical injuries were severe: burns from pyroclastic material, wounds from debris carried by the tsunami, respiratory damage from ash inhalation. The psychological injuries were less visible but no less real, and they would persist long after the physical wounds had healed. The global consequences of the eruption were becoming apparent even as the local consequences were still being measured. The volcanic aerosols injected into the stratosphere by Krakatoa's paroxysmal explosion began to affect climate on a planetary scale almost immediately. In the months following the eruption, average global temperatures dropped by an estimated 1.2 degrees Celsius, a seemingly small number that represented, in practice, a significant disruption to weather patterns, agricultural cycles, and ecosystems across the northern and southern hemispheres. The effect persisted for roughly 5 years before the stratosphere gradually cleansed itself of the suspended material. The sunsets produced by the aerosol veil became, paradoxically, one of the eruption's most widely documented effects in the developed world. In Europe and North America, the months following August 1883 produced evening skies of extraordinary color, vivid reds, purples, and oranges that lasted long after the sun had dropped below the horizon. These sunsets were painted, photographed, and written about extensively. Scientists in England, attempting to explain them, began the investigations that would eventually contribute to the modern understanding of how volcanic eruptions interact with global climate systems. The painter Edvard Munch, who witnessed these unusual skies in Norway in the years following the eruption, is believed by some art historians to have drawn on their unsettling quality in the creation of his most famous work. The world was changed. Not temporarily inconvenienced, changed. And the place where the island had stood was not finished with change. Beneath the waters of the new caldera, in the silence and darkness of the seafloor, the processes that had built Krakatoa in the first place had not stopped. They had only paused. The child of Krakatoa, the sea does not forget what lies beneath it. In the years following the eruption of 1883, the waters of the Sunda Strait returned to something resembling their ordinary character. Ships crossed again. Trade resumed. The colonial administration rebuilt what it could along the damaged coastline. And the slow, persistent work of recovery proceeded in the way that human communities have always recovered from catastrophe. Imperfectly, incompletely, but forward. The towns that had been destroyed were not all rebuilt. Some locations were simply abandoned, their former existence marked only by the absence of what should have been there. But life along the strait continued, and within a generation, the eruption of Krakatoa had passed from immediate trauma into historical memory. Beneath the surface of the water, however, nothing had stopped. The magmatic system that had fed Krakatoa's eruption in 1883 remained active. The subduction of the Indo-Australian plate beneath the Eurasian plate continued at its measured, geological pace, generating the heat and the volatile rich magma that had always found its way toward the surface at this location. The caldera on the seafloor, the depression left by the collapse of the island's northern section, was not an ending. It was an opening, a new configuration of the volcanic system, a reshaped pathway through which the processes continuing at depth would eventually express themselves again. In 1927, 44 years after the destruction of Krakatoa, fishermen working in the strait reported unusual activity in the area where the island had stood. Bubbling water. The smell of sulfur. Discoloration of the sea surface in patterns consistent with submarine volcanic activity. Scientists were alerted, and in late December of that year, a new island emerged from the water within the boundaries of the old caldera. It appeared, collapsed back beneath the surface, and appeared again. A pattern that repeated several times over the following months as the new volcanic structure built itself up and was repeatedly destroyed by the interaction of its hot material with the surrounding seawater. This cycle of emergence and collapse is common in the early life of submarine volcanoes. And the scientists observing the new activity understood that what they were witnessing was the resumption of a volcanic system that had never truly ended. By 1930, the new island had stabilized sufficiently to remain above the waterline. It was given a name that acknowledged both its origin and its nature: Anak Krakatau. In Indonesian, the name means child of Krakatoa. Anak Krakatau grew steadily through the middle decades of the 20th century, adding material through periodic eruptions that, while significant by ordinary standards, were modest compared to the events of 1883. It became one of the most closely observed volcanoes in the world, a subject of continuous scientific interest precisely because of its history and because its behavior offered a living laboratory for the study of volcanic processes in an environment shaped by one of the most dramatic geological events of the modern era. Researchers from Indonesian institutions and international universities visited regularly. Monitoring equipment was installed. The island became, in a strange way, both a scientific resource and a kind of geological monument to what had preceded it. It also continued to be dangerous. In December of 2018, Anak Krakatau demonstrated, with sudden and terrible clarity, that the lessons of 1883 had not been fully absorbed by the modern world. A flank collapse on the southwestern side of the island, the partial failure of the volcanic edifice into the sea, generated a tsunami that struck the coastlines of Java and Sumatra with little warning on the evening of December 22nd. The wave arrived at night, during a holiday weekend, when beaches and coastal areas were populated with people who had no reason to anticipate danger. More than 400 people were killed. Thousands were injured. Coastal infrastructure was severely damaged. The 2018 event was, in geological terms, a modest occurrence compared to 1883. The flank collapse that generated the tsunami involved a fraction of the material displaced by the paroxysmal eruption of the parent volcano. But it was a powerful demonstration of a principle that volcanologists had understood for decades and that public awareness had not fully internalized. The dangers associated with Krakatoa were not historical. They were ongoing. The child of the volcano carried the same fundamental risks as its parent, expressed through the same geological mechanisms in the same geographically vulnerable location. The 2018 tsunami accelerated investment in monitoring and early warning infrastructure across the Indonesian archipelago. The network of seismic sensors, GPS stations, tide gauges, and satellite monitoring systems focused on Anak Krakatau and the surrounding region was expanded and improved. The Indonesian government, working with international scientific partners, invested in public education programs aimed at coastal communities, teaching the recognition of tsunami warning signs, establishing evacuation routes, conducting drills in towns and villages along the strait. This work is ongoing. It is also incomplete. The challenge of protecting human populations from volcanic and tsunami hazards in a region as geographically complex and densely inhabited as the Indonesian archipelago is one of the defining problems of modern hazard science. The coastlines that face Anak Krakatau across the strait are home to millions of people. The economic and practical realities of life in coastal communities mean that even well-informed populations make decisions that prioritize immediate livelihood over long-term risk. The sea remains, as it has always been, both the source of life and the potential instrument of destruction for the communities that live beside it. Anak Krakatau continues to erupt periodically. It continues to grow. It continues to be monitored by instruments and observed by scientists who understand, better than anyone who stood on the shores of the Sunda Strait in August of 1883, what a volcano in this location is capable of producing. The child is still young, and the earth beneath it has not changed its nature. What the earth remembers there is a particular kind of knowledge that only catastrophe can produce. It is not the knowledge found in textbooks or accumulated through careful experiment, though it eventually finds its way into both. It is the knowledge that arrives when the assumptions underlying an entire civilization's relationship with the natural world are stripped away in a single morning, when the ground that was understood as solid reveals itself as temporary, when the sea that was understood as bounded reveals itself as capable of crossing every boundary human hands have drawn. This is the knowledge that Krakatoa produced in 1883, and its reverberations have not stopped moving through the sciences, through the policies, and through the collective understanding of what it means to live on an active planet. The eruption of Krakatoa was, among many other things, a founding event for modern volcanology. In its immediate aftermath, the Royal Society of London undertook one of the most comprehensive scientific investigations ever conducted into a natural disaster up to that point in history. The committee assembled by the Society spent 2 years collecting accounts, measurements, barometric records, tidal gauge readings, and physical evidence from locations around the world. Their report, published in 1888, ran to nearly 500 pages and addressed the eruption's effects on atmospheric pressure, ocean waves, global temperature, optical phenomena, and acoustic propagation across the planet. It was a work of extraordinary intellectual ambition, and it established methodological standards for the scientific investigation of volcanic events that shaped the discipline for generations. The barometric data collected in 1883 confirmed, for the first time with rigorous instrumentation, that a single geological event could send a measurable signal through the entire global atmosphere. The pressure wave from the paroxysmal explosion was recorded at stations on every inhabited continent, circling the globe multiple times and remaining detectable for days. This finding fundamentally altered the scientific understanding of the relationship between geological events and atmospheric dynamics, a connection that now lies at the heart of climate science, atmospheric modeling, and the study of how volcanic eruptions influence global temperature patterns over time. The tsunami records collected after 1883 similarly advanced the understanding of how ocean waves are generated and propagated by sudden geological displacements. The tide gauge readings from stations around the Indian Ocean and beyond provided the first comprehensive dataset of a tsunami's global reach, demonstrating that these waves could remain coherent and measurable across oceanic distances far greater than had previously been appreciated. This understanding, refined through subsequent events and modern instrumentation, is the scientific foundation upon which today's tsunami early warning systems are built. The optical phenomena produced by Krakatoa's stratospheric aerosol veil, the vivid sunsets, the unusual sky colors, the apparent changes in the color of the sun and moon observed across the northern and southern hemispheres in the months and years following the eruption, drove the development of what would eventually become atmospheric optics as a formal scientific discipline. The investigators who attempted to explain these phenomena in 1883 and 1884 were working at the edge of what physics could then describe, and their efforts to construct explanations pushed the boundaries of understanding in ways that proved consequential for subsequent science. Beyond the specific scientific advances, Krakatoa's eruption contributed something more fundamental to the human relationship with the natural world. It demonstrated with a completeness that no previous event had matched that geological processes operating on timescales and scales entirely beyond human control could intervene in human affairs without warning and without the possibility of negotiation. The eruption did not discriminate between colonial administrators and local fishermen, between the educated and the uneducated, between those who had studied the volcano and those who had never thought about it. It expressed itself, and the human world in its path absorbed the consequences. This is not a comfortable knowledge. It sits uneasily alongside the confidence in human agency and technological capability that has characterized modern civilization's self-understanding. But it is an honest knowledge in the civilizations that have absorbed it most fully, that have built their warning systems and their evacuation plans and their building codes and their coastal management policies and genuine acknowledgement of what the Earth is capable of are the ones that have demonstrated the capacity to reduce, if never eliminate, the human cost of geological events. Indonesia today operates one of the most sophisticated volcanic and seismic monitoring networks in the world, a necessary infrastructure for a nation that sits atop one of the most geologically active regions on the planet. The lessons of 1883 and 2018 are embedded in that network's design, in the protocols that govern its operation, and in the ongoing work of the scientists and emergency managers who maintain it. Those lessons are also embedded in the memories of coastal communities along the Sunda Strait, not always in formal or articulated ways, but in the lived knowledge passed between generations about what the sea can do, about what certain sounds and certain behaviors of the water mean, about when to move and where to go. Krakatoa is not a closed chapter. The volcano that produced the loudest sound in recorded human history is not silent. Its child continues to grow in the middle of the strait, adding material through ongoing eruptions, reshaping itself slowly and continuously in the manner of all volcanoes that are alive. The tectonic processes that created it operate on timescales that make human history seem brief, to the point of insignificance. The plate beneath the strait will continue to descend. The magma will continue to rise. The island will continue to evolve. What we carry forward from 1883 is not despair at the indifference of geological forces to human life. What we carry forward is the harder and more useful understanding that preparedness is not the elimination of risk, it is the honest acknowledgement of risk translated into action taken in advance of the event rather than in response to it. The earth does not issue warnings in language we were born knowing how to read. Learning to read them is the work of every generation that chooses to live beside the fire. And we have always chosen to live beside the fire.